Welcome back to my series on making a game engine called Midpoint. So far, we have set up concept generation, file syncing, and the wgpu pipeline. Since Midpoint is AI-centric, this video will cover generating, storing, and loading 3D models into our wgpu scene. Let's begin with our image grid, which features concepts generated in a previous video. You can check the GitHub repo for any gaps in the code you might see. It starts by simply looping through the file data, displaying a preview with the associated CloudFront URL along with the saved file name. You can see the beginning for our Generate Model button, which allows for easy model generation from concept images. Now we have the on-click handler for that button. It's a rather typical handler for this application. It features the 3D model data from the API, transforms it slightly, then saves it locally, after which it will be synced just like the images. I'll cover all of the related functions next. Here we have a typical GraphQL call. It accepts the URL to the image, which is unique and unguessable, but tied to each asset stored in our game engine project. We also have this simple helper function for updating the extension on the file name, as we expect GLB from the Replicate API. GLB is just GLTF in a binary form, which means it's more lightweight to transport and not human readable. Now we have the save model handler in the background process. As in other videos, the sync directory is hard-coded for now, although the models directory is dynamic. We simply clean up the provided data, decode it, and then save it to a file. The separate file manager application will handle the syncing of the model. Back in the U side, we can update our component to display another grid for the models. This is very similar to the concept image grid, but only contains a button to add the model to the scene. If we jump into our wgpu code, we can add the relevant function for updating our renderer state with the new model. I cover the renderer state in the pipeline setup video of this series. We have a few things going on here. First, we pause rendering during this very fast process of adding a model to the scene. This is only a safety feature. Next, we take advantage of Mutex's guard technique to ensure that we can safely update the renderer state within a spawned process while rendering. It is used in tandem with the drop function near the bottom. Inside the spawned process, we simply read in the model data from the background process, then pass those bytes to the renderer state add model function. Here we have the read model handler in the background process. It's a very simple function to read the bytes directly, but WASM does not allow this functionality on the front end, which is why we moved it to the background process. Now, if we check out the renderer state, we can add the add model function. It just creates a new model as a struct and pushes it into the renderer state properties. Next, we have the actual model struct and its associated components. Technically, each model is divided into separate meshes, so that's how we set up our structure. Each mesh will be drawn during our frame rendering, covered during the pipeline setup video. I won't dive into the details of each property on the mesh struct, but these are common properties for anything rendered in our scene. We need the transform, the buffers, and the bind groups to render. Now we can get into the implementation of the model. This is the function we leverage when adding a model to the scene. Using the provided bytes and the GLTF Rust crate, we are able to leverage the functionality it provides. Depending on your version, we could be breaking changes with my code, so be sure to check out the GitHub for contextual information. In the event that our models contain actual image texture data, rather than color data for each vertex, we can handle that here. GLTF provides easy functions for interacting with textures, so it's no trouble pulling in related metadata. We also create a wgpu texture as is standard practice. After creating a texture, we also need to write the texture to the queue. Finally, we create our texture view and sampler as well, just with the default settings. Our generated models will not actually contain image textures, so this portion is not critical yet. Now, as we continue on this function, we need to create some default texture view, and sampler. This is necessary when we aren't using these, but the shader expects them to be bound anyway. Next comes the loop, which does most of the work for this function. We take advantage of GLTF to extract all of the data we need, including positions, colors, normals, and texture coordinates. Thankfully, 3D file formats often store their data in easily extracted structures. We use this critical information to build the vertices required for rendering, as well as read in the indices, which pull all of the vertices together. We wouldn't get anywhere without creating our buffers and bind groups for rendering, so we do that here. Finally, we create the bind group depending on if image textures are used with this model. Since we aren't expecting image textures, we are likely to pass in the default data for this bind group, while the required data is stored in the vertex buffer. To wrap up this function, we push each mesh into a vector along with the default position and return the model itself. That's almost it. We can now generate a model, store it, and then add it to our wgpu scene. However, let's quickly circle back around to the server-side code. Here is a GraphQL resolver. Much like a REST endpoint, which simply takes the CloudFront URL image path and calls replicate. Inside our helper class, we can see how we call TripoSR from the replicate client. You'll want to remove the backgrounds so the generated models come out clearly. And here's how we get the base64 encoded data for the model as well, which is ultimately passed back to the application for saving. That about covers it. Hopefully, you are excited for the direction of this game engine as well, putting AI and UX at the center. If you learned anything from this video, be sure to subscribe. Thank you.